Hello everyone. Today we're going to be covering graphing skills in physics. Graphs are really important in physics and science in general. The idea behind, or the motivation to make a graph when you have data is that when we're in physics, we're looking for relationships between two different variables. So if I increase this, what happens to this other thing? And the best way to visualize that relationship between those two variables is through a graph. I don't know about you, but I can't really I can't really glean any information from a data table. It just doesn't do anything for me. I'm just staring at a bunch of numbers. It doesn't mean anything. But when you graph those two variables against each other, you can quite clearly see what relationship there is between them, if any. So the skills you need to know to graph data in physics are scaling an axis, plotting points, drawing a line of best fit, calculating slope, and interpreting slope. So let's go through those one by one, and we'll talk through best practices for doing this yourself when you are making your graphs. So scaling an axis is the first skill we need to learn. And scaling an axis means making each box on the graph worth an appropriate value so that the data is accurately represented. Each box needs to be worth the same amount. So if if in between the first and second box you make that a 5, then the next gap has to be a 5, and the next gap has to be a 5 all the way up. And our goal here is to scale it in such a way that we include all of the data in a reasonable space. So my rule of thumb is you need to fill up at least half of the graph space. Okay, so let's go and see what this is going to look like. Let's see some bad examples first. So this is a very bad graph. This is poorly scaled. We've got Arkansas football wins. The year is on the x-axis and the number of wins is the y-axis. And this is a bad graph because it's poorly scaled in the vertical axis. We can clearly see that every data point is under 25. And yet, our graph on the vertical axis, our scale goes up by 25s, up to 100. There's no reason for that scale on that vertical axis to go up to 100. There's no data points anywhere close to that. So we would be much better served to, let's say, go up by, let's say, 5s. So what we could do instead, let's say, is 5, 10, 15, 20, and then maybe we would have to add one up here, 25. And then our data would nicely fill in that space, because as it stands, that doesn't really give us any information. It doesn't show us any clear trends. Like, yeah, we can see down here that maybe there's a little bump here, and then a dip, and then a bump, and then a bump here, and a dip here, but we don't get to see how dramatic those bumps are unless we scale it properly and we really bring all that data into a good visual field. So this is bad. It does not take up at least half the graph space on the vertical axis, so don't do this. The other version of bad graphing is is not using a break. So this is a graph that is poorly scaled and the axes were poorly labeled because all of the data is clustered over here. And again, I don't think we can glean that much information from this tiny cluster of points. Yeah, maybe they go up and to the right a little bit, but we're not really seeing the full trend in the data. Is it a straight line? Is it not a straight line? What's the deal? So this graph is interesting to me because whoever made it did one thing right on the y-axis, and that was make a break. So a break is where you start at 0 and then you split and you skip a whole bunch of numbers until you get to the number that you want to start with. So instead of writing every number from 0 to 280, they'd made a break. So we said, all right, we're going to go 0, skip a whole bunch, right? Here's our break. And then we're going to go up by 5s because that's the data that we actually have. It starts at 255, makes it up to a little bit under 280. So what the makers of this graph should have done is done the same thing and made a break on the x-axis. So if they broke on the x-axis, and we can see that one of our points is a little bit behind 100, so maybe we start at 90, 95, 100, 105, 110. Maybe that would be a good scale. And then we could more accurately see how these data points are scattered, and maybe we can get a better sense of what the trend in the data actually is. So that's a bad graph. Don't do that. Use a break if you have to. All right, now let's talk about how to scale an axis. So what we're going to want to do is we need to see, first of all, how much graph space do we actually have. We want to count the number of boxes on the x and the y axis. Then you're going to look at the span of your x and y data. What is the smallest point and what is the largest point? And you're going to need to choose a box value that puts your smallest data point close to the bottom left and your largest data point at the top right. So we need to, again, take up at least half the graph space, and you need to make sure that your scale allows all data points to be plotted. You don't want any data points to be off the graph. That's not good either. We don't want to cramp our data, and we don't want to extend it too far off the graph. So let's get an example here. I've got dissolved oxygen levels at various temperatures. We have water temperature in Celsius and levels of dissolved oxygen in parts per million. We also have a graph space provided for us, which is nice. We've got dissolved oxygen levels at various temperatures. They labeled the graph appropriately, and they labeled the axes, right, which you should always do. You have to label your axis so that the reader knows what data is actually being plotted on that axis. So water temperature is down here, and dissolved oxygen is up here. And I'll pause for a second here and talk about which thing you should graph on which axis. So the x-axis, the horizontal axis, is always going to be what's called the independent variable. And the independent variable, when you're taking actual data in science, I like to say that the independent variable is the thing that you can directly control. If you can push a button or turn a knob or do something to change that variable directly, that's going to be your independent. On the y-axis, the dependent variable is the thing that is supposed to change when you change the x-axis, the independent. So when I do something to the x-axis, the independent, something should happen to the dependent on the y-axis. The only exception to this is that when you are measuring something against time, so time moving forward, so for instance, I could say, I've got a car and I want to plot where it is at any point in time. So I measure its position at 1 second, I measure its position at 2 seconds, 3 seconds, and so on. Time would always go on the x-axis because it is the independent variable. You can, in this case, you can't control the passage of time, right? A second is always a second, but the time is, or the position is dependent on the time measurement. But let's go ahead and let's look at this data. So we're going to look first at the x-axis. What's our data span? We're going from 1 to 30, all right? So let's count our boxes and let's see what we have. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. All right, we have 18 boxes. We don't have to use all of them. We should use most of them, though. So I think that a good way to get from 1 to 30 is to make each box worth 2. And that will enable us to go up by 2s all the way to the, and the 15th square will represent 30, right? 15 times 2 is 30. So let's go ahead and do that. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. So the graph space that I'm not using is over here. Right, we're not using that graph space, and that's okay. We're still taking up at least half of the grid space, which is good. All right, now let's look at our vertical, our dependent. We're going from 7, that's not a 7, 7 to 14. So let's count how many boxes we have on the vertical. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay. So we have 15, and we're going from 7 to 14, so we can make each box worth 1. That's fine. So 2, 4, 6, 8, 10, 12, 14. Okay. So now we have properly scaled our axis. And we're going to be able to fit all of our data in a very nice, pretty grid space. It's not going to be too cramped. We're going to have no points that are off the grid space, so this is a good scale. Next, we're going to plot points. So remember that plotting points, those points are in an x, comma, y format. Generally, the data table will tell you which goes on the x and the y if you're not sure. Again, the independent variable goes on the x and the dependent variable goes on the y. So if we're looking at our graph here, we've got some points. So I'm going to go ahead and plot those. We're at, so 114. That goes up here. Okay. 10, 11. So 10 up to 11. We've got 15, 10. So 15, 10. 29. So 29. 25, 8. 25, 8. And 37. So 30 and then 7. All right. So those are our data points. So they're nice, pretty data points. They look like they're in a pretty straight line. But let's talk about the next thing we're going to have to do for graphing. And that is a line of best fit. So a line of best fit shows the trend in a data set. It will, hopefully everything that we do will end up in a straight line. We generally try not to deal with any sort of curves, quadratic functions, parabolas, things like that, sine waves, or sine functions. So the line of best fit should be a line, ideally. And the rules here are the line of best fit has the same number of data points above and below it, and the line should not cross through any data points. So let's go back to our graph. All right, our line of best fit is going to look something like that. Okay, and so what have we done? Well, I can see that this is above, below, below, and then these two are kind of on the line, which is not perfect, but that's okay. So we have made an adequate line of best fit for this data. Next, scoot forward. We're going to look at slope, calculating slope. Hopefully this is not news to you. Slope is defined as rise over run, where rise is the change in y value and run is the change in x value. This can be written as y2 minus y1 over x2 minus x1, where again, x is the independent variable and y is the dependent variable. Now, the key here is we're going to choose the points for the slope from the line of best fit, not two actual data points. So you're going to use your line of best fit. And the reason why this is helpful is because, let's go back to our graph. The line of best fit touches grid squares or intersections of grid squares where some data points might not. So some good points that we might want to take to do our slope might be right here. That's pretty close. And then another one could be something, no, that's not too super. Something like right here, okay? So those are close to the grid squares, and that allows us to calculate some slope. So let's do that. Let's write our points. So that first point up there is 4, 13, and then this other one is 18, 9. Right, that seems just about right. So notice these, again, these are not two actual data points. They are data points from the line of best fit. So if we're going to do y2 minus y1 over x2 minus x1, that's going to look like 18 minus 4 over, oh, I'm sorry, nope. Yeah. Right. y2, I'm sorry. 9 minus 13, I got my brain scrambled, over 18 minus 4. So that's going to be 9 minus 13 is a negative 4, I think. Sure, why not? Over, and 18 minus 4 is a 16, which reduces to a negative 1/4 slope. So that is our slope. Okay. Pause for kind of comprehension here. All right, so let's see. I think that's it. Okay, yes. So we'll go back. So that's everything. What did we do? We scaled some axes. We plotted points. We found a line of best fit, and we calculated slope from the line of best fit. So what you're going to do now is you're going to have a classwork and a homework that are basically just exactly the same thing that I just did for you. You get a data set and a blank grid space. You have to scale your axes, plot points, line of best fit, and calculate slope. You'll do that twice, one on the classwork, one on the homework. Upload them to Teams, and that will be it for the day. So thanks for paying attention, and I will see you later.